Okay, let's talk about independence. Now, here's the general definition. After the general definition, we'll tell you what it means for discrete and continuous random variables. In general, random variables are independent if their CDF, if their joint CDF is the product of the individual CDFs. Okay, that's kind of hard to intuit. So let's look at discrete and continuous separately. If we have a set of discrete random variables and discrete random variables, then they're independent if the PDF, probability distribution function, probability mass function, is the product of probability mass functions. And let me just skip ahead. For continuous random variables, it's similar. If we have continuous random variables, then the joint PDF of the random variables is the product of the individual PDFs of the separate random variables. Now, based on this formula, it shouldn't be surprising that the expectation also factors in the same way, that the joint expectation of these n random variables is equal to the product of the expectations of the individual random variables. Okay, so let's do some practical examples of independence and see what this actually means. So how about we start with two discrete random variables. And we'll say that x, remember a random variable is like an experiment. So x means that Joy throws throws coin 5 times. And counts the number of heads. Okay, and we'll say y is, well, let's do x1 and x2, because we've been doing that. x1 is this, x2 is Roy throws 3 coins, throws a coin 3 times and counts the number of tails. Okay, now notice that these two experiments have nothing to do with each other. So they really do satisfy the criterion that we would call independence, that intuitively we would think of these two things as independent. Okay, so let's look at the probability distribution functions of these two. Now I think you should be familiar with the distribution of number of coins. This is going to be a binomial probability with probability 1/2. So if we do the px1 of x, that's going to be equal to 5 choose x times 1/2⁵, and that's for x equals 0 up through 5. And the probability that x2, this is just going to be 3 choose x. I'm using the same variable x, it really doesn't matter, times 1/2^3. Okay. Now, what's the probability, and here I'll just say x1, x2, of x1 and x2? Well, what are the possibilities? We could draw the possibilities in the plane. We could have, if this is the x1 value and this is the x2 value, x1 can take values from 0 up to 5. X2 values can take 0 through 3, but for each x2 value, we can have these 6 x1 values, 0, 1, 2, 3, 4, 5. Okay, so here we have 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and then here, 1, 2, 3, 4, 5. Okay. Now, if we wanted the probability of any one of these points, if I wanted the probability of x1, x2, of getting Joy getting 2 heads and Roy getting 1 tail, that's just going to be, you just multiply the probabilities. That's a very simple way of thinking about it. It's going to be equal to 5 choose 2 times 1 over 2 to the 5th times 3 choose 1 times 1 over 2 to the 5th. And I can combine 1 over 2 to the 3rd, rather. And I can combine the 1 over 2 to the 5th and the 1 over 2 to the 3rd to get 1 over 2 to the 8th. Right. Now notice something about when you have this independence. If I take these probabilities and I consider them as a vector, okay? If I consider these probabilities here as a vector, and I consider these probabilities as a vector, what's the difference between these two vectors? Okay. Well, for instance, what's the ratio of this probability to this probability? Well, the ratio is the same as the ratio of the probability that x2 is equal to 2 divided by probability that x2 is equal to 3. Okay, that's the only difference between these two probabilities. The x1 value is the same. So the only difference in the probability is the value of the probability x2 that it's multiplying. What's the ratio of these two values? Well, these two outcomes are the same, except this one has x2 equal to 2, this one has x2 equal to 3. So again, the ratio is the same. Probability x2 equals 2 divided by probability x2 equals 3. Okay, so we do the same thing. So these two vectors are in constant ratio. If you remember linear algebra, you can see that these are linearly dependent. They're multiples of each other. And the same would hold true for this vector, and the same would hold true for this vector. So what would that mean? Suppose I drew the probability mass function just for these points. So suppose I do the PMF where x2, we'll say x2 equal 2. All right. Now, if you think about how this works, these values 0 and 5 are not common. These are more common. These are the most common. In fact, if you want to get this 5 choose x here, a good trick is Pascal's Triangle. If you haven't seen this, you do the triangle, you put 1s at the first and the last, then every other entry is the sum of the two entries around it. So that's going to be 2, and I put a 1 at the end. I put 1 here. 1 plus 2 is 3. 2 plus 1 is 3. And here I have 1. Here I have 1, 4, 6, 4, 1. Then I have 1, 5, 10, 10, 5, 1. Okay. So if I plot the PMF when x2 is equal to 2 right here, let me just put this in red so I can outline it. All right, that's going to be the values of x1 can be from 0 to 5. Okay, and these values are going to be in this ratio. This is going to be, this one is going to be 5 times as big. This one's going to be 10 times as big. This is 10 times as big. This is 5 times as big. This is 1 time as big. Now, what the actual heights are, you'd have to multiply by the probability that x2 is equal to 2. Okay, but the ratios of these heights are going to look exactly like the ratios here. Okay, what's the PMF when x2 is equal to 1? Okay, well, we have to compare the heights. We can do the Pascal for n equal 3. Well, actually, that's this one, 1, 3, 3, 1. I'll just do it again. 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay, actually, so that means that this value of x2 is 3 times more likely than this value of x2. Okay. So if I were to draw the PMF for this row across, every height would be 3 times as high as this one. It would be exactly the same shape, but the heights are 3 times as big. Okay, so let me just indicate that. 3 times here, this one is going to be 3 times as big as that one. Next one is going to be 3 times as big as that one. And same with this one, and then this one, and then this one. I can say all heights are 3 times as big as the x2 equals 2 heights. Okay, so in a sense, these two, when you have independence, you have similar cross sections. If I take a cross section of this distribution, just look at this constant x2 value, I'll get one cross section. No matter which horizontal slice I take, the PMF is going to look similar. It will be scaled up and down by different heights, but it's going to look similar. Same if I slice it vertically. If I slice it vertically, I'll also have similar cross sections. Okay, so the shape of the distribution this way is constant, independent of x1. The shape of the distribution this way is constant, independent of x2. Okay. So I can say it's constant shape. Okay. All right, that's for discrete. Suppose I do continuous. Okay. Now, we were saying that if you have independent random variables, you have a product distribution. So in this case, we have f of x1, x2 of x1, of little x2, would be equal to, say, f1 of x1 times f2 of x2. Okay, so let me do a famous example. And we'll use this distribution called the Gaussian distribution, 1 over square root of 2. Well, sorry, that's going to be my f1. Is equal to 1 over square root of 2 pi. And then I'm going to have a sigma 1. Sigma 1 is actually turns out to be the standard deviation of this distribution. Then I have e to the minus x1 minus mu1 squared. So this turns out to be the standard deviation. And this turns out to be the mean. And here I divide by 2 sigma 1 squared. And suppose I have f2. Well, suppose I have f2 is similar, except I have a sigma 2. Here's a mu2 squared divided by 2 sigma 2 squared. All right. Now, if I were going to get a joint distribution, what would that look like? Well, it's going to be a continuous distribution in the x1, x2 plane. And I'm going to draw a contour line so you can see kind of what's going on here. If the mean of this one is mu1, mean of this one is mu2, there's going to be a point here, mu1, mu2, where the PDF is maximum. And then around that, the contour lines, the lines of constant probability density, will look something like this. There'll be ellipses like this. Kind of like a mountain. Looks like a mountain. Okay, and I draw ellipses. This, for any ellipse, this axis here is proportional to sigma 2. And this axis is proportional to sigma 1. Okay, so if sigma 1, in this case, sigma 1 is big, sigma 2 is small, the bigger the sigma, the more spread out the distribution is. Okay, now if I were to take any cross-section of this distribution, what would I see? Well, I'd see something called a bell-shaped curve. Okay, let me draw it a little bit better. Okay, I'm going to draw it a little bit tighter. Okay, so this is going to be the x1 equals c cross-section. Okay, and no matter what cross-section I take in this direction, it's going to look like this. Now suppose I take a cross-section in the other direction, that would be taking a cross-section this way. And this maximum point would be along this line where, so this dimension is actually x2, and this is where x2 is equal to mu 2. So this is similar to a Gaussian distribution, and this half width here, this would be sigma 2. Okay. So if I take a x2 equals c cross-section, I'm going to have my constant point at where sigma 1 is, where x1 equals mu 1. Now, since the variance or standard deviation is larger in this direction, the density is going to be more spread out. Okay, I'm sorry I didn't draw this very well. That's supposed to be maximum there. Let's do it again. I'll fudge it so I make sure that I get a maximum here. So this is sigma 1, this is mu 1, okay. And you can see sigma 1 is bigger than sigma 2. Okay. So think of this as a mountain, right? This is a kind of a bell-shaped mountain. And every cross-section is similar, which mountains are sort of like that. It's probably more like a hill than a mountain because there's no peak. Okay. Right. So this is called a two-dimensional Gaussian distribution. And this is the case where x1 and x2 are independent. If x1 and x2 are independent, then the Gaussian distribution looks like this elliptical shape, which is either horizontal or it could be vertical if sigma 2 was greater than sigma 1. Okay, well, the last thing I'm going to do is show you why show you why this expectation formula works. Actually, I can show it on this page here. What is the expectation of x1 through xn? Well, that's going to be the integral of my PDF. I'll use continuous. The similar proof for when the random variables are discrete. I'm going to use my PDF. I'm going to use my x vector shorthand for my PDF, for my joint PDF. This is going to be times the variables x1 up to xn. And you multiply this by x1 up to xn. That's how you can find expected value of a random variable. So you take the random variable, multiply it by the PDF, and you integrate. Now I write the dxn first because we're doing inside out. That's through dxn through dx1. Okay. Now, the bottom line is that this PDF can be written as a product. If it can be written as a product, then the first term here, x1, doesn't depend on any variable except x1. Similarly, this x1 only depends on x1, so I can pull that out into an x1 integral. I can do that with every single variable. Say x2, right? The x2 dependence of this density only depends on this factor. If I pull this factor out together with the x2 here, integrate it by the dx2, I get a second factor. So I can actually write this as the product, this means product, It's like sum, but it's product. So this is from I equals 1 to n. And then for each one of these variables, I'm going to have an integral. This is an integral minus infinity to infinity, so just for FYI. So in each case, I'm taking the product of the integral, and this is going to be f of x, xi of xi times xi dxi. All right. Now, what is this here? This is just the product. This quantity here, that's just the expectation of xi. Right? So that's why the expectation of the product is the product of the expectations. Okay, so I'm going to stop there.